Hi friends, in this tutorial I'll be talking about decision trees, how decision trees works and how do they learn. So you might have come across decision trees words a lot maybe because this is one of the most commonly used algorithm in data science or machine learning. Decision trees can be used for regression as well as classification, but more generally this is used for classification. And in this tutorial as well I'll be talking about how decision trees works in terms of classification only. So this can be used for binary classifications like a person is going to be turned into defaulter or not, or a person is gonna have a cancer, having a cancer or not, etc., etc. You know classification, right? So yeah. So how does this work? So decision tree generally, as all algorithms, tries to find the relation between independent variables versus dependent variables, but a decision tree does that by expressing them in terms of a tree structure. So you might have also come across binary trees in DSA, right? So you'll also find a similar structure over here as well. So how does it perform? So I'll give you a short example. So let's say we have a car data in which you want to say buy it or not, and it has different attributes like color, model, which year, what is the mileage or what is the brand, etc., etc. Very small. This is how a decision tree looks like generally. So what it does is, given independent features, it tries to make conditions. It tries to learn the condition which is able to segregate or make the data or samples homogeneous. So as let's say, this is one condition. Color is red, yes or no. If it is yes, then I will check model is greater than 2010 or not. If it is yes, then I'll buy that. If model is not greater than 2010, I'll check no and I'll check another condition, which is mileage. If the mileage is less or more. And similarly here, if color is not red, then yellow. If yellow, yes, then is it Ferrari or not. If not yellow, then I don't even want to buy. So I mean, this was just a glimpse of like how a decision tree looks like. It's very naive, but yeah. So let's go to direct example and maybe just see how we can split based on the independent variables and dependent variables, how we can make conditions on it. So here I took an example of data, like I just randomly filled it. So two independent variables like eat lots of pizzas and age, and one dependent variable or my target column is fitness. It's fit or not. So based on if the person is eating lots of pizza or not and what is his age, we want to determine the fitness of the person. So let's take this data. Here I have 4 unfit and 5 fit. So I want to split such that in my final branch I have all similar, will come all same target values, mostly same or most homogeneous. I think you'll understand when I explain more. So let's split the data based on our eat lots of pizza independent variable. So if eat lots of pizza, yes or no. So I just splitted the data into 2 parts. So wherever it was yes, I put it in here, and wherever it was no, distributed here. Remember, this is a learning process, how a decision tree learns. So it tries to make conditions, and then in those conditions it tries to check whichever has the final highest homogeneity. Homogeneity in the sense like more of a similar class in my target. So here, as I said, out of 4 unfits, it has 3 unfits and 2 fits, and when you eat lots of pizza, out of 4, it has 3 fits and 1 unfit. So this is how I splitted my 2 data, but still you can see there is 1 unfit and 3 fit, and there are 2 fits and 3 unfits. So we can split again this data. So let's split again. Let's split the upper one and the lower one separately. So let's split the upper one first. Eat lots of pizza, yes. In this, I'm gonna check the age. If age is less than 21, split it, make it one part, and if the age is greater than 21, make it the another part. So as you can see, I have two different sets now, and in this you can see I have same target values in the separated or splitted data. So if the each lots of pizza is yes and age is less than 21, the fitness is fit. But if the age is greater than 21, the fitness is unfit. By the way, don't take offense in this data. I just put it randomly. Okay. So now similarly, we will split the bottom part of the data when eat lots of pizza is no. So we'll check the age again here. If age is less than 50, I split the data in one part, and if age is greater than 50, I put the data in another part. It should be greater than equal to, but yeah. So here you can see all three fits came in single and one fit. So I'm able to segregate my sample targets, and in all those segregation my targets are more or less same. It's same in this case, but sometimes it might not be same, and you don't need to split further. Maybe like there are 6 unfits but one fit. It's okay. The whichever has the highest one will be considered as the final one. So as you can see here, it's already segregated. We don't need to split anymore. So this is how our final decision tree would look like for this particular data. So let's see if this is the training. This is how it was learned. What are the conditions it should check. Now, given a inference script, how does it work in an inference? So you'll get one sample in which you want to infer where each lots of pizza is yes and age is 20. You want to predict fitness. So how decision tree would look like in this case? Input data will come. Eat lots of pizza yes or no. Yes. In this case yes. And then we'll check the age. What is the age? Age is less than 21? Yes. So our final is fit because as you can see in our previous one, age less than 21 and eat lots of pizza is yes, our final is fit, right? So we have the fit one. So this was the inference decision tree, and this is how our final overall decision tree looks like for the previous data. So input data we check each lots of pizza is yes or no, and based on age we have unfit, fit, unfit, fit. I hope it's clear till now. So the cart, this like scikit employs a cart algorithm to create binary trees to split these nodes. I mean, so you can read on this how this cart algorithm works and all. So this is how a basic decision tree looks like and how the basic inference works on in decision trees. But there are few issues in decision trees, right? So by default, decision tree will try to build a tree where the smallest child nodes are perfectly homogeneous. So smallest child nodes, what does it mean by that is my final these, right? As you can see, and these are my final child nodes, and it will try to make it homogeneous. So let's say even if there was one unfit and fit, it will again create a node. So it will kind of overfit the data on training data. So this is one of the issue. The classes in each leaf node it would like to have same because it will try to make it fully homogeneous. But the issue in this case is it's trying to overfit the data. If some inference some sample comes, it might not work as same as it should. It might not work good. So, and also to achieve homogeneity, each leaf has one record. Such models are same thing. So to overcome these issues, we can have some conditions or some parameters to make it not too overfit. So there are few parameters like we can fix the maximum depth of the tree. So let's say in this case we had a depth of 1 and 2. So whatever the conditions are, like on the number of conditions in each level, right? Sorry, the number of conditions it has, so 1 and 2, so it has 2 depth. So we can fix the depth. Let's say if we have fixed the depth to 1 right here, so we wouldn't have learned till this. So we have only checked eat lots of pizza, yes or no, and based on that we have checked unfit. There are 3 majorities unfit, so we will label it as unfit. So that's how we can make it to not overfit. That is one of the things. Second is we can set the minimum number of samples present in leaf node. So in leaf node, right, generally it tries to split to make it homogeneous. So we can make it such that in leaf node I should at least have this number of labels, so that it doesn't have only single record in leaf node to make it it as overfit. As in previous case, you can see here we has one single, right, but this should not be the case. So here we can reduce it, reduce the overfitting. One more thing, there are other algorithms which are built on decision trees to make it robust and make it more make it less overfit, like random forest, ADA boost, bagging. I'll be talking about these algorithms in a different tutorial. So let's see now again, how does it learn? How does it choose a condition through which we can just segregate or we can split the data? How does it choose which is the best condition at that point, so that I can split my data on that particular condition? So in decision trees, they use a loss function which it tries to minimize or optimize. As same as in any machine learning algorithms, we try to minimize or optimize some particular loss function. So in this decision tree, as I was talking about homogeneity, right, it has loss function such that the homogeneity in each child node increases. So what is a child node again? Sorry, I didn't explain it. So this is my root, and these are child nodes, and the last part are the leaves, and these are called branches. Again, yeah. So we do this. We do increase homogeneity using two things. We have entropy and Gini. These two kind of losses which can be used to calculate homogeneity at a particular level. So assume there are 100 balls in a box, out of which 50 are white and 50 are black. You want to pull one of the ball. You know, right? 50-50. So there are like 50-50 probability. So it's the highest uncertainty. We don't have any certainty like I'll get a white ball or black ball. It's highest uncertain because it's exactly 50-50. If there was 60 white balls and 40 black balls, getting white would be little bit more certain than black, but still there is still uncertainty because of the probability we know 0.6, 0.4. But let's say when the bag has all white balls and I know for sure that whatever I'll be picking, it will be white, so there is no uncertainty. So in the end, decision tree's goal is to make uncertainty as close to zero as possible. So uncertainty and homogeneity here kinda related to each other. So this can be expressed using entropy and Gini index. So let's see what is entropy, what is Gini. So entropy here is like Shannon's entropy, you might have heard or not, but the formula of that is the sigma probability log of probability, and all these are negative because log of decimal log of 0 to 1 is negative number, that's why we have a. So this is how entropy looks like. It's kind of a negative summation of px into log of px, and px is nothing but the probability in that particular child node. Like let's say if there are 4 unfits and 1 fit, so the probability of unfit is 4 by 5 and probability of fit in that is 1 by 5. So we'll do this summation on all. So 4 by 5 into log of 4 by 5 plus 1 by 5 into log of 1 by 5. So we'll do the calculation in the. I'll show you an example of this. And there's something called Gini as well. So the range of entropy is from 0 to 1. So the 1 means like it has very much uncertain, and 0 means its uncertainty is 0. Similarly, Gini index is like 1 minus summation of the square of probabilities. So as I said, 4 by 5 unfit and 1 by 5 fit. So 4 by 5 square into 1 by 5 square. 1 minus that. So Gini, the range of Gini goes from 0 to 0.5. So let's say an example. Imagine there is in a bag there are 6 black balls and 4 white balls. So what is the entropy in that particular scenario? So entropy, as I said, negative of the probability into log of probability. The base is 2 here. The base of log is 2 in entropy here. So the probability of black ball is 0.6, which is 6 by 10, 0.6, log 2 of 6, 0.4, log 2 of 0.4. And it comes around 0.97. Whereas Gini in this case is 1 minus square of 0.6 plus square of 0.4, which is 0.48. Suppose we have all orange balls, and then the entropy and Gini in that case would be, you can see all are orange, so it's 1, and there is nothing, so 0. So log of 1 is 0. So as you can say, entropy came to 0. And Gini came to, it should be 1 minus 1, it should be 0. That is my bad, I'll update that. But yeah, this Gini would also be 0. 1 minus 1 is 0. So let's see one more example. So information gain on entropy. So now these are like entropies and Gini are like, tells us how much uncertainty is there, right? But now from previous to this one, how much I have gained or how much the uncertainty is reduced. So that is told by information gain. It's nothing but simple like reduction in entropy. So my reduction from root node, like 1 at depth equal to 1 is high, let's say 0.8, and the next is 0.6. So I gained 0.2 of information. So let's say I'll give an example here. So assume there are 100 samples of wine, out of which 60 samples belong to class A and 40 samples belong to class B. Like this. So the entropy in this case is, as we calculated, 60 by 100, 0.6, and 40 by 100, 0.4. This is 0.97. Now I applied some conditions. Let's say some condition on that independent features, and I got 50 for class A and 10 for class B in one of the child node. So this is child node, and this has 10 of that class A and 30 of class B. So let's calculate the entropy of these two separately. So the entropy in this node would be 50 by 60, because 50 is class A and total are 60, into 2 log of, same formula, and 10 by 60 because class B is 10. So this comes around 0.65. And in this case, the entropy would be, you can say 10 by 40 because 10 is class A and total 40. So similarly, it comes around 0.81. It's not visible here probably. I'll share the link to the PPT. So the information gain is IG. Information gain is reduction in entropy from here to here, from this level to this level. So as it's a binary tree, it will only split each node to 2. You remember that. So the entropy in this case is 0.97 in this level, and in this level the entropy is, so total there are 60, right? So we'll also have the probability or the weighted, this is like the weighted sum of the entropy of here plus here. So there are 60 samples in this case and 40 samples in this case. So 60 by 100 into 0.65 plus 40 by 100 into 0.81. So information gain is around 0.256 on entropy. Similarly, there is information gain on Gini index as well. It's same thing. Only thing is we'll be calculating Gini in terms of entropy. Same thing. Let's assume the same example. We have 0.48 here, which the maximum Gini can go is 0.5. So the range is from 0 to 0.5. That's why. So Gini in this level is 0.48. Gini for this particular child node is 1 minus 50 by 60, as the formula is sum of probability squares. It is coming around 0.277 because, as you can see, it's more homogeneous compared to this, because there are 50 from class A and 10 from class B, right? Here also it's less than this, but it's more than this, but still, yeah, let's calculate. It's coming around 0.375. So again, the information gain is reduction in Gini, and the Gini at this level would be the weighted sum of this plus this. So let's say 0.48 is from this level minus the weighted sum of 0.28, this one, into 0.6, and 0.4 into 0.375, which is coming around 0.162. So we say that the information gain from my previous node to this node is this much. So what it does is, what decision trees does is, it tries to apply different conditions in this level. So it had tried different conditions, and it calculates information gain on each of those conditions, okay? And finally it will take the condition which has the highest information gain at that particular level. So let's say this example, if it was let's say some other condition would be maybe 40, 20, and let's say 20 and 25. Sorry, 20 and 20. I know that this is less homogeneous, right? So that would have less information gain compared to this one. And this was the best information gain I could have got using different conditions. So yeah, so at each level it applies different conditions on different independent features, and then it calculates the information gain using this formula. And whichever has the highest information gain, whichever condition has the highest information gain, we select that, and that condition is used in the inference. Like we did for age is less than 20, age is greater than 21, right? It might have also tried age is greater than 30, age is less than 30. But in that case, the information gain might have been less because of the homogeneity or because more uncertainty. So yeah, that's how decision trees learns, like, or collects which condition is right condition at that particular level. So the advantages and disadvantages of decision trees are, again, simple, fast and process effective, because in inference you see it will just go blah 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 blah. It just follow the path in the tree, right? In inference, so nothing complex, can work with missing data. So yeah, one thing in this is decision trees can learn from missing data as well. What it does it, for that particular sample, it checks, I mean, if something called surrogate splits is the concept. What it does is, let's say some condition is there where, yeah, let's say each lots of pizza is yes, okay, but in one of, what if there are missing data in that? So what it does, it tries to have the similar, it gets a different condition which has the similar behavior of my primary split. Primary split means primary condition. So it tries to make another condition which has almost similar correlation with the my primary condition for that particular task. So that's how it can handle missing values as well. It can handle both numeric and categorical values, as I have shown, like eat lots of pizza is categorical and age is numerical. So interpretation of results is much easier. when represented as rules, as we saw, like that car, like car color, mileage and all. It's very easy to see and just follow. But there are again disadvantages of this, because often biased towards features which have large number of levels. Large number of levels means that it has large number of distinct values. So the trees gets biased because it tries to keep on making conditions on that particular level itself, or particular feature itself. So that is one of the disadvantages of it. Small change in training data can result in large changes to the logic. Yes, because a single condition can be affected if the training sample, if we add different samples. So yes, it is highly, it changes, the logic changes based on the training data. Again, decision trees tend to overfit and by default creates large and complex trees. As I have told you, it tries to make a homogeneity as good as possible. So in trying to do that, it creates large and complex trees, and those large and complex trees are very hard to interpret, or difficult to interpret. So that's it on decision trees. It's very like basic stuff I have explained through. I'll also go through I'll go through random forest and bagging boosting, which are nothing but algorithms are made from decision trees. So for that, this is one of understanding decision tree itself makes important for to understand those three different algorithms. So yes, I'll share the link to this PPT as well. You can go through if you want. If you have any comments, you can write and if you have any questions, you can write in the comments. I'll reply as soon as possible. Thank you.